March 12, 1943. The morning sun cast long shadows across the Rechlin test facility's main hangar, 90 kilometers north of Berlin. Oberingenieur Walter Hoffman removed his leather gloves as he approached the captured American aircraft that had arrived 3 days earlier. The P-38's Lightning, tail number 42-12652, sat under armed guard, its distinctive twin-boom configuration drawing curious stares from every Luftwaffe technician who passed. The aircraft had been forced down near Bizerte, Tunisia, on February 28 after taking battle damage during an escort mission. Feldwebel Otto Richter's maintenance crew had managed to recover it largely intact, one engine damaged beyond repair, but the other perfectly preserved, along with its mysterious supercharging system that German intelligence desperately wanted to examine. Hoffman had spent 15 years designing aircraft engines for Daimler-Benz. He understood supercharging theory better than almost anyone in Germany. Yet the preliminary reports from Tunisia made claims that seemed impossible. The Americans had allegedly designed a system that allowed their fighters to operate effectively above 40,000 feet, altitudes where German fighters gasped for air and lost all combat effectiveness. The mathematics seemed wrong. The engineering appeared fantastical. But the evidence was about to reveal a truth more devastating than any tactical defeat. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The systematic examination of the P-38's power plant would expose not just a technological breakthrough, but a fundamental philosophy about high-altitude warfare that Germany had failed to understand. The Americans had solved a problem that German engineers insisted could not be solved with existing technology. They had created an operational high-altitude fighter, while Germany still struggled with experimental prototypes that would never reach mass production. The capture had begun on February 28, 1943, in the skies above Tunisia. Second Lieutenant James Morrison of the 1st Fighter Group had been escorting B-17 flying fortresses targeting the port facilities at Bizerte when his Lightning's starboard engine took a direct hit from German anti-aircraft fire. The Allison V-1710 disintegrated in a spray of oil and metal fragments, but Morrison kept flying, the port engine's turbocharger still functioning perfectly. He nursed the crippled aircraft toward Allied lines, but German ground fire had also punctured his coolant system. Temperature gauges climbed into the red zone. Morrison realized he would never reach friendly territory. He put the Lightning down in a dry riverbed, 15 kilometers behind German lines, belly landing with enough skill to keep the airframe largely intact. German troops reached the crash site within an hour. Morrison was already gone, beginning a 3-day evasion attempt that would end with his capture on March 2nd. But the Lightning remained, and Feldwebel Richter immediately recognized its intelligence value. He ordered his recovery team to work through the night, disassembling the undamaged engine with extraordinary care. The engine arrived at Rechlin on March 9th, packed in wooden crates and accompanied by technical documentation that Richter's men had found in the aircraft's storage compartments. The American maintenance manuals were remarkably detailed, with clear diagrams and specifications that assumed minimal technical knowledge from users. German manuals, by contrast, required readers to understand complex engineering principles. Hoffman assembled his examination team on March 12th. With him were specialists in supercharging, metallurgy, fuel systems, and engine controls. They began with external inspection, carefully documenting every component, every connection, every design detail that differed from German practice. The Allison V-1710 was a liquid-cooled 12-cylinder engine of 1,710 cubic inches displacement. This much German intelligence already knew. What they did not understand was how the Americans had mated this relatively conventional engine to a turbocharging system that apparently allowed sustained operation at altitudes where German fighters could barely maintain level flight. Oberleutnant Hans Weiss, the team's supercharging specialist, focused immediately on the General Electric Type B13 turbocharger mounted in the rear section of the engine nacelle. He had studied captured documents about American turbocharger development, but this was his first opportunity to examine the actual hardware. The turbocharger sat in a streamlined housing behind the engine, connected by exhaust pipes that channeled hot gases from the engine's exhaust manifold to the turbine wheel. The turbine, spinning at tremendous speed, drove a compressor that forced pressurized air into the engine's carburetor. This allowed the engine to maintain sea-level power output at high altitudes, where atmospheric pressure normally strangled performance. Weiss carefully measured the turbine housing. The dimensions were larger than anything used in German aircraft. The turbine wheel itself, when he finally removed the housing for inspection, was a masterpiece of metallurgical engineering. The blades were precision cast from a nickel-chromium alloy that could withstand temperatures exceeding 700 degrees Celsius and centrifugal forces that would tear apart lesser materials. He ran his finger along one blade's surface. The finish was nearly mirror smooth, reducing aerodynamic losses to absolute minimums. Each blade was identical to the others within tolerances, measured in hundredths of a millimeter. This was not laboratory equipment. This was mass-produced hardware installed in thousands of operational aircraft. Hoffman joined Weiss at the examination bench. Together, they studied the turbine's construction. The precision was extraordinary. The balance was perfect. The materials were exotic alloys that German industry could produce only in small quantities for experimental applications. Yet here they were, used casually in a standard production fighter engine. "How fast does this rotate?" Hoffman asked. Weiss consulted the captured technical manual. According to American specifications, the turbine reaches approximately 24,000 rotations per minute at maximum boost pressure. At that speed, the blade tips exceed 1,500 feet per second velocity. Hoffman did the mathematics in his head. At such speeds, even minor imbalances would tear the turbine apart. The precision required to manufacture a wheel capable of surviving such conditions exceeded anything in German production capability. He noted in his preliminary report that this single component represented manufacturing sophistication Germany could not match. The examination continued deeper into the supercharging system. The team discovered an intercooler, a heat exchanger that cooled the compressed air before it entered the engine. Hot compressed air is less dense than cool compressed air. By cooling the air after compression, the Americans increased the mass of oxygen entering each cylinder, providing more power. German engineers understood intercooler theory. The Daimler-Benz DB 605 engine, used in the Bf 109G, incorporated intercooling. But the American implementation was more sophisticated, using a larger core with more efficient heat transfer and lower pressure drop. The intercooler was not hand-fitted by skilled technicians. It was a standardized component, mass-produced with specifications that ensured consistent performance across thousands of engines. Oberleutnant Weiss traced the plumbing that connected turbocharger, intercooler, carburetor, and engine. Every joint used standardized fittings. Every clamp was identical. Every hose followed the same routing. An untrained mechanic could disassemble and reassemble the entire system using only basic tools and the illustrated manual that accompanied every aircraft. German engines required skilled mechanics who understood the theory behind what they were doing. American engines were designed so that any reasonably competent soldier could perform maintenance by following simple procedures. This philosophy reflected completely different assumptions about how to wage industrial warfare. The fuel system revealed even more sophistication. The Allison used a Bendix-Stromberg pressure carburetor that automatically adjusted fuel flow to match air density at any altitude. German carburetors required manual mixture adjustments as aircraft climbed or descended. American pilots simply set the mixture control to auto-rich, and the carburetor handled everything automatically. This automation was achieved through a complex system of aneroid barometers, springs, and metering jets that sensed air pressure and adjusted fuel flow accordingly. The mechanical complexity was significant, but it transformed a pilot's workload. German pilots constantly monitored engine instruments and adjusted mixture settings. American pilots focused on flying and fighting while their engines managed themselves. By the end of the first day's examination, Hoffman's team had documented the external characteristics of the turbocharging system. They understood how it worked in principle. What they did not yet understand was the full implication of what they were seeing. The second day began with operational testing. The team mounted the Allison engine on a test stand, equipped with instruments to measure power output, fuel consumption, exhaust temperature, and manifold pressure. They connected the engine to compressed air supplies that could simulate any altitude up to 45,000 feet. Hoffman initiated the start sequence following procedures from the American manual. The Allison coughed once, then caught with a smooth rumble that settled into a steady idle. He advanced the throttle gradually, monitoring dozens of gauges and sensors. The engine responded smoothly, power increasing linearly with throttle position. At full throttle and sea-level simulation, the engine produced 1,325 horsepower, according to the test stand dynamometer. This matched German intelligence estimates for the Allison V171049 variant, but the real test would come at altitude. WWII adjusted the altitude simulation system, reducing air pressure to match conditions at 15,000 feet. The engine's power output began dropping as the thinner air provided less oxygen for combustion. Then Hoffman activated the turbocharger control, increasing boost pressure to compensate for the reduced atmospheric pressure. Power output climbed back toward sea-level values. The turbocharger was maintaining manifold pressure as altitude increased, exactly as designed. They continued climbing in simulation. 20,000 feet, 25,000 feet, 30,000 feet. At each altitude, Hoffman increased turbocharger boost to maintain engine power. At 35,000 feet, the Allison was still producing over 1,200 horsepower. German fighters at this altitude could barely manage 600 horsepower from engines that produced 1,400 horsepower at sea level. The Americans had solved the altitude problem completely. WWII checked the turbine inlet temperature. It was approaching design limits, but still within acceptable parameters. The turbine was spinning at nearly 24,000 rotations per minute, compressing air to over twice atmospheric pressure, even at 35,000 feet altitude simulation. They pushed higher. At 40,000 feet, the engine was still producing 1,000 horsepower. This was more power than the Daimler-Benz DB 601 inches the early Bf 109E could produce at sea level. The Americans were generating full combat power at altitudes where German fighters became helpless targets for any enemy who could reach them. At 44,000 feet, the altitude where American bomber formations had been reported operating, the Allison finally began losing power despite maximum turbocharger boost. But it was still producing approximately 850 horsepower, enough to maintain level flight and maneuver effectively. German fighters at this altitude produced less than 400 horsepower and could barely maintain altitude, let alone fight. Hoffman shut down the engine and sat in silence for several minutes, absorbing what they had discovered. The test data was irrefutable. The Americans possessed operational fighters capable of effective combat at altitudes the Luftwaffe could not reach. The implications cascaded through his mind like dominoes falling. Every German fighter design was optimized for combat between 15,000 and 25,000 feet. The Bf 109G's critical altitude, the point where its supercharger could no longer maintain sea-level manifold pressure, was approximately 22,000 feet. Above that altitude, performance degraded rapidly. The Focke-Wulf W190A, Germany's other frontline fighter, was even worse at high altitude. Its BMW 801 radial engine with mechanical supercharger lost power above 20,000 feet. Attempts to improve high-altitude performance with the Fu 190D variant were still in development and would not reach operational units for many months. Meanwhile, the Americans were flying formations of B-17 and B-24 bombers at 25,000 to 30,000 feet, escorted by P-38 Lightnings that could cruise at 30,000 feet and climb to 44,000 feet if necessary. German interceptors struggled to reach these altitudes, and when they did, they had minimal power for combat maneuvering. The third day of examination focused on the turbocharger's control system. WWII discovered an automatic regulator that maintained specified manifold pressure regardless of altitude. The pilot set desired boost pressure with a control in the cockpit, and the regulator adjusted turbine speed automatically by controlling exhaust gas flow to the turbine. This automation was achieved through a pressure-sensing controller connected to a butterfly valve in the exhaust system. If manifold pressure dropped below the set point, the controller closed the bypass valve slightly, forcing more exhaust gas through the turbine, increasing turbine speed and boost pressure. If pressure exceeded the set point, the controller opened the bypass slightly, reducing boost. The entire system operated continuously, making thousands of tiny adjustments per minute to maintain precise pressure control. German pilots manually adjusted boost pressure and carefully monitored gauges to avoid overboosting, which could destroy an engine in seconds. American pilots set the control once and focused on flying. Hoffman's team documented every aspect of the regulator system. The components were precision machined from corrosion-resistant materials. The linkages were wear-resistant. The pressure sensors were temperature-compensated for accuracy at any altitude. Everything was designed for reliable operation by minimally trained users in harsh combat conditions. The metallurgical examination of the turbine wheel revealed, perhaps the most disturbing findings. Dr. Friedrich Koch, the team's materials specialist, performed detailed analysis of the nickel-chromium alloy used in the turbine blades. The alloy composition included elements that were critically scarce in Germany. Nickel, chromium, and molybdenum were essential for high-temperature applications, but Germany's access to these materials was severely limited. Nickel came primarily from Norway and Finland, chromium from Turkey and Greece, molybdenum from limited domestic sources. The Americans apparently had no such constraints. They were using exotic high-temperature alloys in applications where Germans would have used cheaper alternatives. A single P-38 turbine wheel contained more strategic alloying materials than an entire German fighter engine. Dr. Koch calculated that the United States had installed turbochargers in approximately 10,000 P-38 aircraft by early 1943. Each turbocharger required exotic alloys for the turbine wheel, housing, and high-temperature components. The total consumption of strategic materials for P-38 turbochargers alone exceeded Germany's entire annual production of similar alloys. Where were the Americans getting these materials? Intelligence reports provided the answer: unlimited access to global resources. Nickel from Canada, chromium from Southern Africa, molybdenum from massive deposits in Colorado. American production of strategic materials exceeded Axis production by factors of 5 to 10 in most categories. Hoffman's report to Luftwaffe headquarters, completed on March 18, 1943, ran to 147 pages of technical analysis, photographs, and strategic assessment. The conclusions were devastating. The Americans had developed a practical, reliable, mass-producible turbocharging system that provided high-altitude capability German engineering could not match with existing technology. The P-38 Lightning could operate effectively at altitudes up to 44,000 feet, beyond the reach of any German interceptor in service or development. Most critically, the turbocharging technology represented a complete system approach to high-altitude flight. Engine, supercharger, intercooler, control systems, and materials were all designed to work together as an integrated whole. Each component was optimized for mass production, ease of maintenance, and reliable operation by average users. German high-altitude fighter development, by contrast, proceeded piecemeal. Different companies developed engines, superchargers, and airframes independently. Coordination was poor, resources were limited. Each prototype required hand-fitting of custom components by skilled technicians. Hoffman estimated that Germany would need at least 3 years to develop comparable turbocharging technology, assuming unlimited resources and no interference from Allied bombing. With actual constraints of materials, manufacturing capacity, and ongoing combat operations, practical deployment of German high-altitude fighters equipped with operational turbochargers was unlikely before 1946 or 1947. The report reached Reichsmarschall Hermann Göring's desk on March 25, 1943. It was classified Geheime Kommandosache, secret command matter, and distributed to only 12 senior officers in the Luftwaffe Technical Command and Reich Ministry of Aviation. The response was predictable denial. Several recipients questioned Hoffman's conclusions. Perhaps the captured engine was an experimental prototype, not representative of production aircraft? Perhaps the Americans had only a few high-altitude fighters, insufficient to affect the strategic situation. These objections were addressed by intelligence reports from combat units. Luftwaffe fighter pilots were encountering P-38 Lightnings regularly in Tunisia and Sicily. Every captured example showed the same turbocharging system. Serial number analysis suggested American factories had produced thousands of these engines. More disturbing reports came from Germany itself. On March 18, 1943, the same day Hoffman completed his report, American B-17 bombers attacked the U-boat construction yards at Vegesack near Bremen. The bombers flew at 27,000 feet, higher than German fighters could effectively intercept. On April 17, B-17 seconds struck the Focke-Wulf aircraft factory at Bremen from 28,000 feet. German fighters struggled to reach the bombers, and those that did found themselves at such high altitude that combat maneuvering was nearly impossible. The bombers' defensive firepower, combined with German fighters' degraded performance, resulted in heavy Luftwaffe losses for minimal bomber casualties. The pattern was becoming clear. American bomber formations were deliberately climbing to altitudes where German interceptors could not effectively engage. The turbocharging technology examined at Rechlin was enabling a strategic bombing campaign that operated beyond Germany's defensive reach. Major Adolf Galland, General der Jagdflieger, General of Fighter Pilots, received Hoffman's report on March 28, 1943. Galland had extensive combat experience and understood tactical realities better than most Luftwaffe commanders. He grasped the implications immediately. If American bombers could operate at 30,000 feet or higher, German air defenses would be largely ineffective. Existing fighters could intercept at those altitudes, but only by sacrificing everything else: fuel, ammunition, endurance. They would arrive at combat altitude with barely enough power to maintain formation, let alone engage in the violent maneuvering that aerial combat required. Galland initiated urgent development programs for high-altitude interceptors. The Focke-Wulf TAR-152H, the Messerschmitt Bf-109H, and eventually the jet-powered Me-262 all included high-altitude capability as a primary design requirement, but development, testing, and production would require years. Meanwhile, American bombers continued operating with near impunity above 25,000 feet. The daylight strategic bombing campaign that Germany had weathered somewhat successfully in 1942 became devastating in 1943 as American formations climbed beyond effective interception altitude. The examination of additional captured P-38 components continued through spring and summer 1943. Each discovery reinforced the same conclusion. American engineering had solved the high-altitude problem through systematic application of advanced technology and unlimited resources. An intact P-38G captured in Sicily in July 1943 showed improvements over the earlier F model. The turbine wheel used an even more exotic alloy with improved temperature resistance. The intercooler was larger and more efficient. The automatic regulator incorporated refinements that improved response time and accuracy. The Americans were not just building high-altitude fighters, they were continuously improving them, incorporating lessons learned from combat operations and advancing the technology with each new production batch. German development, constrained by limited resources and competing priorities, could not keep pace. Oberleutnant Weiss transferred to a high-altitude research facility in Bavaria in August 1943. His new assignment was developing turbocharging systems for German fighter engines. He brought detailed knowledge from examining American equipment, but that knowledge only emphasized the gap Germany faced. The turbine wheels Germany could produce, even in small quantities for experimental applications, could not match American mass production components for quality or reliability. The exotic alloys were simply unavailable in required quantities. The precision manufacturing equipment needed to produce turbine blades to American tolerances did not exist in German factories. Most frustratingly, even if Germany solved all technical problems, the production capacity to build turbochargers in meaningful quantities was not available. American factories produced thousands of turbocharged engines monthly. German factories struggled to produce dozens of experimental units. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By autumn 1943, Luftwaffe intelligence had documented the complete scope of American high-altitude capability. It was not just the P-38, the Boeing B-17 and consolidated B-24 bombers, both used turbocharged engines, the Wright R-1000-820 Cyclone, and Pratt & Whitney R-1000-830 Twin Wasp, respectively. Both engine types incorporated General Electric turbochargers, similar to the system used in the P-38's Allison. This meant that American heavy bombers had genuine high-altitude capability, not just the ability to reach high altitude briefly, but to operate there for hours, maintaining formation, conducting bombing runs, and defending against interceptors. The turbochargers allowed bomber engines to maintain full power at 30,000 feet, something German bombers could not achieve. The strategic implications were profound. Germany's air defense system, built around fighters optimized for medium-altitude combat, was obsolete. The Americans had simply climbed above it. Worse, there was no quick solution. High-altitude interceptors required new engines, new supercharging systems, new materials, and new production facilities. None of these could be created quickly. Oberingenieur Hoffman left Rechlin in December 1943 to join the Emergency Fighter Development Program at Focke-Wulf. His assignment was advising on high-altitude power plant requirements for the TAR-152 interceptor. He brought intimate knowledge of American turbocharging technology and the sobering awareness that Germany could not replicate it. The TAR-152H, when it finally reached limited production in late 1944, used a mechanically supercharged Junkers Jumo 213E engine with a three-stage supercharger and MW50 methanol water injection for boost. It was a sophisticated solution to the high-altitude problem, but it was not turbocharging. It could not match the P-38's ceiling or sustained high-altitude performance. More critically, only approximately 150 TAR-152H aircraft were produced before the war ended. The Americans had built over 10,000 turbocharged P-38 seconds by that time, plus thousands of turbocharged bombers. One side had solved high-altitude flight as a mass-production engineering problem. The other had created an experimental solution that arrived too late and in too few numbers to matter. The story that began with Hoffman opening the nacelle of a captured P-38's March 1943 concluded with Germany's air defense system in ruins by early 1945. American and British bombers roamed German skies almost at will, striking industrial targets, transportation networks, and civilian centers with devastating effect. German fighters still flew, still fought, still scored victories, but they fought at a hopeless disadvantage. American bombers climbed beyond effective interception altitude. When German fighters struggled up to engage them, they arrived with engines gasping for air, barely capable of maintaining altitude, let alone executing the violent maneuvers that combat required. The P-38 Lightning, flying escort at altitudes German fighters could barely reach, destroyed interceptors with impunity. The twin Allison engines, each with its General Electric turbocharger spinning at 24,000 rotations per minute, maintained full combat power at 40,000 feet while German pilots below struggled with engines producing half their rated output. The technological gap that Hoffman's team had identified in March 1943 only widened as the war progressed. By 1944, American factories were producing turbocharged engines at rates that exceeded total German aircraft production. The gap was not just technological, it was industrial, organizational, and ultimately strategic. German engineers understood turbocharging theory as well as their American counterparts. In some areas, German theoretical knowledge exceeded American understanding. But theory does not win wars. Production capacity wins wars. The side that can build thousands of high-altitude fighters, while the enemy builds dozens, will control the skies above 25,000 feet. The Americans had demonstrated this principle with devastating effectiveness. The human cost of Germany's high-altitude disadvantage was measured in thousands of young pilots who climbed desperately toward American bomber formations, only to find their fighters unable to close the final few thousand feet of altitude. Engines overheated, controls became mushy, stall speeds increased, combat became impossible. Lieutenant Werner Schröer, who would survive the war with 114 victories, described the frustration of high-altitude interceptions in his combat memoir, written decades later. He recalled missions where his Bf 109G climbed for 20 minutes to reach 28,000 feet, only to find American bombers cruising comfortably at 32,000 feet, with P-38 escorts above them at 35,000 feet. Schröer's aircraft, at its absolute ceiling, could barely maintain altitude. Any combat maneuvering caused immediate altitude loss. The P-38 seconds above him, by contrast, had power to spare. They could dive, zoom, climb, turn, and maintain complete energy advantage over any German fighter that ventured into their realm. He wrote that engaging under such conditions was suicidal, yet orders demanded that they engage. German pilots climbed into hopeless situations day after day, knowing that American turbocharging technology had rendered their aircraft obsolete for high-altitude combat. Some returned. Many did not. Major Heinz Baer, eventually credited with 220 victories, developed specific tactics for high-altitude interceptions. He realized that German fighters could not fight American escorts at altitude, so he focused on the bombers themselves. His tactic was to climb to maximum altitude well ahead of the bomber stream, then make a single high-speed diving attack through the formation. The dive gave German fighters temporary speed advantage. Baer's pilots would plunge through the bomber formation, fire one burst at the closest target, then continue diving to lower altitude where their engines could produce adequate power for maneuvering. They would not attempt to engage P-38 escorts at all. This tactic occasionally succeeded in downing bombers, but it was hardly an effective defense. A single pass with minimal time for accurate shooting, then immediate disengagement. American bomber formations absorbed such attacks and continued to their targets. The strategic bombing campaign proceeded regardless of German tactical adaptations. By winter 1943 to 1944, Luftwaffe intelligence had obtained additional examples of American turbocharging technology. A B-17G forced down near Schweinfurt in October 1943, provided intact Wright R-1820 Cyclone engines with their turbochargers. A B-24H that crash-landed near Regensburg in February 1944 yielded Pratt & Whitney R-1830 engines. Each examination revealed the same pattern. American turbochargers were sophisticated, reliable, and mass-produced to consistent specifications. The turbine wheels were precision components manufactured from exotic alloys. The control systems were automated. The entire installation was designed for operation by minimally trained crews following simple procedures. The examination teams, now led by younger engineers as experienced personnel like Hoffman, were reassigned to desperate development programs, documented everything meticulously. Their reports filled archives with technical details that would prove valuable to historians decades later, but provided no practical solution to Germany's immediate crisis. Because the fundamental problem was not lack of knowledge. German engineers understood exactly how American turbochargers worked. They could build experimental systems that matched or even exceeded American performance. What they could not do was build thousands of them. Dr. Koch, the metallurgist who had analyzed the P-38's turbine wheel in March 1943, was reassigned to the Junkers engine facility in Dessau in autumn 1944. His mission was developing high-temperature alloys for turbine applications, using only materials available within Germany's shrinking borders. By this point, Germany had lost access to Norwegian nickel, Greek chromium, and most other sources of strategic alloying materials. Koch worked with substitutes, attempting to create alloys that could survive turbine operating conditions using primarily iron and domestic resources. His team achieved some success. They developed alloys that could withstand turbine temperatures for limited periods. But these materials could not match American nickel-chromium alloys for durability, temperature resistance, or fatigue life. A German experimental turbine might survive 50 hours of operation. American production turbines regularly exceeded 500 hours. Even this limited success was meaningless because Germany lacked the production capacity to build turbines in quantity. The specialized casting facilities, precision machining equipment, and quality control systems needed for turbine production simply did not exist. And by late 1944, there was no possibility of creating them. Allied bombing had destroyed much of Germany's manufacturing infrastructure. The Luftwaffe's desperation produced increasingly fantastical solutions. In autumn 1944, several emergency fighter programs received priority development status. The Heinkel He 162 Volksjäger, People's Fighter, was designed to be built primarily from wood by semi-skilled labor and flown by hastily trained Hitler Youth pilots. The concept assumed that Germany could no longer build sophisticated aircraft with strategic materials, so they would build simple fighters from non-strategic materials in huge quantities. The He 162 reached limited production in early 1945, but it was a jet aircraft, not a high-altitude piston-engine fighter, and jets presented their own set of problems that turbocharging could not solve. Meanwhile, American bomber formations continued operating at altitudes where German defenses remained largely ineffective. The 8th Air Force, operating from England, routinely flew missions at 28,000 to 30,000 feet. The 15th Air Force, attacking from Italy, used similar altitudes. German fighters could reach these heights, but only with great difficulty and at severe performance disadvantage. The statistical evidence was overwhelming. In 1942, when American bomber operations remained at medium altitudes accessible to German fighters, Luftwaffe interceptors imposed significant losses on unescorted bomber formations. The Schweinfurt raids in August and October 1943, flown before P-38 and P-51, escorts had sufficient range to accompany bombers all the way to targets deep in Germany, cost the Americans dearly. But by early 1944, when long-range fighters routinely escorted bombers and formations operated at optimum high altitude, German interception effectiveness collapsed. American bomber losses dropped from 7 to 8% of aircraft dispatched in late 1943 to 2 to 3% by spring 1944. The difference was not tactics or training or courage. Luftwaffe pilots in 1944 were as brave and determined as their predecessors. The difference was technology. American turbocharging allowed bombers and escorts to operate at altitudes where German fighters could not effectively engage them. Oberingenieur Hoffman, working at Focke-Wulf through 1944, watched his nation's industrial capacity disintegrate under the strategic bombing campaign enabled by the very technology he had examined in that captured P-38 engine. The irony was not lost on him. In April 1944, the factory where he worked suffered severe damage in an American bombing raid. Production of TAR, 152 components, ceased for 3 weeks while repairs were made. The bombers that attacked flew at 29,000 feet, beyond effective interception altitude. German fighters engaged them, but achieved minimal success. By January 1945, Focke-Wulf production had essentially ceased. Allied bombing, combined with fuel shortages and loss of territory containing raw material sources, made continued aircraft manufacturing impossible. The few TAR 152 aircraft completed were scattered among various units, too few to matter strategically. Hoffman evacuated west ahead of Soviet forces in March 1945. He carried with him copies of his original report on the captured P-38 turbocharger, along with hundreds of pages of subsequent research documenting American high-altitude technology. These documents survived the war and eventually reached American technical intelligence teams. The war in Europe ended on May 8, 1945. Germany surrendered unconditionally. Among the items Allied investigators discovered in abandoned Luftwaffe facilities were the technical reports from Rechlin, now scattered across multiple sites where they had been relocated to avoid bombing. American engineers were surprised by the thoroughness of German analysis. The reports accurately documented every aspect of turbocharger design, manufacturing, and operation. They correctly identified American technological advantages and honestly assessed German inability to match those capabilities. One report, written by Oberleutnant Weiss in November 1944, served as a final testament to Germany's high-altitude disadvantage. Weiss documented that by late 1944, American fighters routinely cruised at altitudes above 35,000 feet during escort missions. German interceptors could barely reach 32,000 feet, and at that altitude they had no combat capability. Weiss concluded that the war in the air over Germany had been lost, not through tactical failures or inadequate pilot training, but through industrial and technological limitations that could never be overcome under wartime conditions. The Americans had solved high-altitude flight as a mass-production engineering problem. Germany had not. This single factor determined the outcome of the strategic bombing campaign. The post-war fate of the German engineers who examined captured American turbochargers reflected the New World Order. Hoffman was recruited by American authorities under Operation Paperclip in 1946. He spent 3 years working for Wright Aeronautical in New Jersey, helping American engineers understand advanced German supercharging concepts. The irony was profound. The man who had documented American turbocharging superiority in 1943 now worked for an American company, sharing German knowledge that Americans might find useful. The transfer of technology flowed in both directions, but the balance favored America overwhelmingly. Weiss joined the French aircraft industry in 1948, working on high-altitude research programs for what would eventually become the French military aviation establishment. He spent the rest of his career developing supercharging systems for jet engines, applying principles he had first encountered examining that captured P-38's 1943. Dr. Koch emigrated to Argentina in 1949, where he worked in the steel industry developing specialty alloys. He maintained contact with former colleagues in Germany and occasionally published technical papers on high-temperature materials. In a 1962 article, he reflected on his wartime work examining American turbine alloys. He wrote that the materials themselves were not particularly revolutionary. The alloy compositions used in American turbochargers were well known in metallurgical literature. What was revolutionary was the American ability to produce them in massive quantities with consistent quality. Germany could make similar alloys in laboratory conditions. America made them in factories employing thousands of workers. This distinction, Koch wrote, defined the difference between the two nations' approach to technology and warfare. Germany sought technical perfection in limited quantities. America sought adequate performance in unlimited quantities. One philosophy could sustain global warfare, the other could not. In 1953, Hoffman published a paper in the Society of Automotive Engineers journal titled Comparative Analysis of American and German Supercharging Philosophy, 1939 to 1945. The paper, based on his wartime experience, provided American engineers with insights into German thinking about high-altitude flight. Hoffman explained that German engineers had focused on mechanical supercharging with multiple stages because they believed turbocharging was too complex for mass production and field maintenance. They assumed that the high temperatures, rotational speeds, and precision requirements of turbine wheels made turbocharging suitable only for limited applications, like bomber engines, where reliability requirements were less stringent than fighters. The Americans proved this assumption wrong. They industrialized turbocharger production using the same mass manufacturing techniques applied to automobile components. They designed turbine wheels that could be cast rather than machined. They developed automatic control systems that eliminated the need for pilot management. They created maintenance procedures that allowed field replacement of failed turbochargers in hours rather than days. Most importantly, American engineers accepted that some percentage of turbochargers would fail in service. They designed the system so that when failure occurred, the engine could continue operating at reduced performance using only its mechanical supercharger. This redundancy meant that turbocharger problems did not ground aircraft. German philosophy demanded near-perfect reliability. Components were over-designed, hand-fitted, and individually tested to ensure they would not fail. This approach produced excellent equipment in small quantities, but it could not scale to the thousands of engines required for global warfare. Hoffman's paper became required reading in engineering schools and influenced a generation of American engineers who designed equipment for the Cold War, the space race, and eventually commercial aviation. The lessons learned from German analysis of American turbochargers shaped American technological development for decades. The specific P-38's Lightning that Hoffman examined in March 1943, tail number 42 to 12652, never flew again. After the engine removal at Rechlin, the airframe remained in storage until it was destroyed during an Allied bombing raid in November 1944. But the intelligence gained from examining that single aircraft influenced Luftwaffe tactical doctrine, strategic planning, and development priorities for the remainder of the war. By the 1980s, many surviving engineers who had worked on turbocharger analysis during World War II gathered for reunions and historical conferences. They shared memories, compared notes, and reflected on their experiences examining technology that represented their nation's eventual defeat. At a conference in Munich in 1987, Hoffman displayed photographs from the original P-38 examination in March 1943. The images showed young German engineers in leather coats and wool uniforms, carefully measuring turbine dimensions, documenting component arrangements, and struggling to understand what they were seeing. Hoffman told his audience that the moment they measured that turbine wheel and calculated the rotational speed it could sustain, he knew American engineering had surpassed German capabilities in critical areas. The turbine was not just a component, it was a symbol of industrial organization, manufacturing sophistication, and resource availability that Germany could not match. A single turbine wheel, a piece of precisely cast nickel-chromium alloy no larger than a dinner plate, represented the intersection of metallurgy, manufacturing, and industrial scale. It was not complex in principle. Any competent engineer could design one, but to produce thousands to consistent quality at acceptable cost required an industrial infrastructure that Germany simply did not possess. That infrastructure, created in America between 1941 and 1945, did not dissolve when the war ended. It expanded and evolved, producing jet engines, rocket motors, and eventually the turbines that powered commercial aviation into the modern era. The same companies that mass-produced turbochargers for P-38 fighters, General Electric, WWII Research, and others, later produced the engines that enabled global air travel. The lessons learned from examining American equipment became foundational to post-war aviation development. Design for mass production. Use automated controls to reduce pilot workload. Accept that some equipment will fail and design for graceful degradation. Build redundancy into critical systems. These principles, visible in every aspect of American turbocharging technology, became standard practice worldwide. In 1995, on the 50th anniversary of the war's end, the Deutsches Museum in Munich opened an exhibit titled Altitude Warfare, The Race for High-Altitude Supremacy, 1939 to 1945. Among the displays was a General Electric Type B-13 turbocharger recovered from a P-38 wreck site in North Africa. The turbocharger sat in a glass case, its turbine wheel removed for viewing. Visitors could see the precision-cast blades, the mirror-smooth internal surfaces, the exotic alloy construction. Beside it, the exhibit displayed a German experimental turbocharger developed in 1944 for the Junkers Jumo 213 engine. The contrast was stark. The American unit was a production component, one of thousands built to identical specifications. The German unit was a handmade experimental device, unique in every detail. Both represented excellent engineering, but only one could be produced in quantities sufficient for modern warfare. The exhibit included excerpts from Hoffman's original report, translated into English and German, explaining what German engineers discovered when they examined captured American equipment. Visitors could read his observations about manufacturing quality, material selection, and design philosophy. They could see photographs of the examination process. The curator's notes explained that the exhibit was not about praising American technology or criticizing German engineering. Both nations had skilled engineers who did their best within available constraints. The difference was resources, industrial organization, and philosophical approach to mass production. Americans designed systems that worked adequately when produced by semi-skilled workers using automated machinery. Germans designed systems that worked brilliantly when built by skilled craftsmen using traditional methods. One approach enabled global warfare, the other did not. The final display in the exhibit was a chart showing American bomber loss rates over Germany from 1942 through 1945. The graph line plunged dramatically in early 1944, precisely when American fighters with turbocharging technology achieved the range and altitude capability to escort bombers throughout their missions. The correlation was undeniable. High-altitude capability, enabled by turbocharging, transformed the strategic bombing campaign from a costly gamble into a sustainable operation that ultimately destroyed Germany's industrial capacity. The technology that Hoffman examined in that P-38 engine in March 1943 determined the course of the air war over Europe. Hoffman died in 1998 at age 89. His obituary in Aviation Week magazine noted his contributions to supercharging technology, his wartime work in technical intelligence, and his post-war career helping American companies understand German engineering innovations. The obituary mentioned his lifelong insistence that Germany's defeat in the air was determined in factories, not in the skies. His papers, donated to the Deutsches Museum, included the original 1943 report on the P-38 turbocharger, plus thousands of pages of subsequent analysis written between 1943 and 1945. These documents provided historians with detailed insight into how German engineers viewed American technology and what they reported to Luftwaffe commanders. Perhaps the most revealing document in the collection was a personal letter Hoffman wrote in April 1945 as American forces approached Focke-Wulf's facilities. He reflected on the 3 years since examining that first captured P-38 engine, years spent trying to develop German equivalents that always remained just out of reach. He wrote that American turbocharging represented not just superior technology, but a fundamentally different approach to warfare itself. The Americans had industrialized high-altitude flight, applying mass production methods to every component, from turbine wheels to control systems. They accepted higher production costs in exchange for superior performance and reduced maintenance requirements. Germany, Hoffman wrote, had tried to achieve high-altitude capability using traditional methods, skilled craftsmen, hand-fitted components, and complex mechanical solutions. These approaches could not scale to the production levels modern warfare demanded. By the time Germany developed working prototypes of high-altitude fighters, America had already built thousands. He concluded with a prediction that proved remarkably accurate. Future wars, he wrote, would be decided by industrial capacity more than battlefield tactics. The side with greater manufacturing capability, more advanced technology, and ability to produce sophisticated equipment in overwhelming quantities would prevail. America had demonstrated these capabilities between 1941 and 1945. Any future opponent would need to match or exceed American industrial power. The Cold War that followed World War II validated Hoffman's prediction. It became a competition of industrial capacity, technological innovation, and manufacturing efficiency. The Soviet Union, despite vast resources and large population, struggled to match American aerospace technology. The gap that Hoffman identified in turbochargers in 1943 expanded to encompass jet engines, rockets, electronics, and eventually computers. The story that began with German technicians examining a captured P-38 engine is ultimately about how industrial capability determines military outcomes in technological warfare. It is about the revolution in manufacturing that occurred in America during World War II, and how that revolution created capabilities that less industrialized nations could not counter. The turbocharger that so impressed Hoffman and his colleagues was not magic. It was engineering, yes, but more importantly, it was engineering scaled to mass production. American industry had learned to produce complex precision components by the thousands, something unprecedented in human history. This capability, developed for turbochargers, extended to every aspect of military equipment and eventually to consumer products. The lessons, learned by German engineers examining American technology in 1943, were harsh but clear. Superior individual equipment means nothing if it cannot be produced in quantity. Sophisticated technology is useless if it cannot be manufactured reliably. Theoretical excellence is worthless if industrial capacity cannot achieve it consistently. These lessons, purchased at the cost of Germany's defeat, became foundational to modern manufacturing philosophy. Design for production, build in quality, automate complex adjustments, scale to demand, support equipment properly. The principles visible in American turbocharging technology now govern manufacturing in every high-technology industry worldwide. In the end, the story that began with Hoffman examining a turbine wheel in March 1943 concluded with complete transformation of how nations prepare for technological warfare. The turbocharger, that precision-engineered piece of spinning metal, became a symbol of industrial warfare's evolution. It represented the moment when victory stopped being determined primarily by tactical skill and started being determined by factory output, resource access, and industrial organization. The German engineers who examined American equipment understood this transformation as it happened. Their reports documented not just technical specifications, but the future of conflict. Today, the principles they identified remain fundamental to aerospace engineering. Turbocharging technology developed for World War II fighters evolved into the turbine engines that power modern aircraft. The industrial philosophy that enabled mass production of P-38 turbochargers became standard practice for manufacturing everything from jet engines to spacecraft components. The direct line runs from that General Electric Type B-13 turbocharger spinning in a P-38's nacelle in 1943 to the turbofan engines on modern airliners. The principles remain unchanged, only the scale has expanded. The German technicians who tested captured American turbochargers in 1943 were not just examining aircraft components, they were witnessing the future of aerospace technology and industrial warfare. Their detailed reports, classified and filed during the war, eventually became historical documents that explained not just why Germany lost control of high-altitude airspace, but how industrial capacity determines outcomes in technological conflicts. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.